turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the show where we bring you the biggest breakthroughs in science, technology and medicine with me, Chris Smith. And this week, Titans of Science continues with planetary scientist Sara Russell. She tells us what it's been like to get her hands on material dating from the origins of our solar system and what it can reveal about where we all came from.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Sara Russell was born in Manchester in 1966. She attended Altrincham Grammar School for Girls in the city before she read natural sciences here at the University of Cambridge, where she specialised in earth sciences. Sara then studied pre-solar grains in meteorites, we'll find out what those are in a little bit, under the stewardship of the great Colin Pillinger at the Open University, and from there she moved to the California Institute of Technology and the Smithsonian Institution before settling at the Natural History Museum in London in 1998. She's participated in multiple expeditions to Antarctica to collect meteorite samples, and she's also been heavily involved with NASA's OSIRIS-REx mission, which collected samples from the asteroid Bennu to provide insights into the early solar system. She's even got an asteroid named after her, and she's joining me today at Queen's College in Cambridge. Welcome back to Cambridge. How did you end up as a space scientist? How did you get into it? Tell us about the path into the subject.
I grew up obsessed with space missions. I would always watch them on TV. I loved looking at the exploration of the moon and of Mars growing up. But I thought I really wanted to be an astrophysicist. I loved physics at school. That was my favourite subject. And I thought that I'd carry on doing physics throughout my career. But then I came here to Cambridge to do a natural sciences degree where you have to try out lots of different subjects. And so I chose earth sciences sort of on a whim. But as soon as I went into the lectures, I was really blown away by it. I didn't know anything about earth science before I came here. And I didn't kind of appreciate that you can look at a rock and you can learn to almost read it like a book. It tells you where it came from. It tells you what history it's experienced. And by studying rocks, you can reconstruct this whole history of our planet. That absolutely blew me away.
And it turned, an astrophysicist into an earth scientist?
Yes, absolutely. Absolutely. I was absolutely hooked. And the lecturers I had around me were all just so passionate about their subject. And they all really wanted to, I think they wanted to recruit all of the physicists, actually. They wanted everyone to love it as much as they did. So this wasn't that long after the discovery of plate tectonics, which had completely revolutionised our understanding of how our planet worked. And so there was still so much to learn, and it felt like a really kind of young and vibrant subject to study.
How did that get you into space, though? Because that's very much feet down here on the ground. But you work now at the Natural History Museum, and how we first met was you were playing around with bits of an asteroid from millions of miles away.
Yes, that's right. So in my final year, we had some lectures on meteorites. So meteorites are any natural extraterrestrial object that has made it to the surface of the Earth. And in particular, we had a guest lecture from Colin Pillinger, who had just moved from Cambridge to the Open University then. And he gave a talk about pre-solar grains. So what he said in his lecture was basically this idea that we're all stardust. So the Big Bang formed the universe 13.8 billion years ago. It produced only hydrogen, and all the other elements around us that we need to make our planet and to make people and plants, to make rivers and oceans, they were all made by stars that kind of are big element processing factories that by doing nuclear fusion, they make all sorts of other elements. And we actually see that inside some meteorites. We see little grains that formed around ancestor stars to ours. And by looking at them in detail, they can tell us exactly what that star was doing, what the exact nucleosynthetic processes were going on, and exactly how we got to be in this planet made of all of these amazing elements.
Presumably, those grains were part of the cloud of gas and dust then that coalesced to form A, the sun, and then B, the clutch of planets that we've got and the asteroids that you're now looking at.
Yes, absolutely. So the idea is our solar system formed from a big cloud of dust and gas that included this dust from old stars and the gases that they had produced when they were dying as well. And this collapsed under its own gravity to form the sun and eventually the planets around it. So that's the very big picture idea of what happened, but we can interrogate that and have a look in much more detail at exactly what happened by looking at meteorites, because they date from the time when all of this was happening. So most meteorites are 4.5 billion years old, and they formed at this time when the sun was just forming and there was a dusty disk around it that the very first solids were starting to coalesce. And just as we can use a rock on Earth to tell us their story, we can use meteorites to tell us the story of what the temperatures and pressures were like at that time and what the composition was like, and just learn about how that process occurred.
How do you date a meteorite? You've just said that some of them are 4.5 billion years old. So you can tell us about your expeditions you did in a minute to Antarctica to find them. But when you do find one, how do you know it's that old?
Yes, so you can find out how old a rock is using radioactive dating techniques. So some radioactive isotopes have half-lives that are similar to the age of the solar system. They have half-lives of billion years or so. And we can use these to look at how much of the daughter isotopes have built up in minerals, and that tells us how old it is. So we can actually age these rocks often very, very precisely to within a few million years or better.
But how do you know how much was there to start with for you to have found it and said, well, one thing turned into another? How do you know how much was there in the first instance?
We know that when the solar system first formed, it almost completely homogenized. So all of the isotopes got really kind of mixed up. So each element ended up with about the same proportion of isotopes most of the time, with a few exceptions. But because we then know what the original isotope ratio was, we can work out how that's evolved over time.
Did that lecture from Colin Pillinger, we're talking about the late, great Colin Pillinger, he created the Beagle 2 mission that went to Mars. It was found more recently, wasn't it, that probe? It went AWOL and luckily was found. That presumably captured you because you became his student.
I did. I actually went up to him at the end of his lecture and asked if he was recruiting. And luckily he said yes. And I ended up doing a PhD with him in the very subject that he had just given the lecture about.
And it was during that time that you went to Antarctica to look for meteorites then?
Yeah, it's over the next few years that I went on several meteorite collecting expeditions. So meteorites land pretty much anywhere in the world, but there are certain parts of the world where if they land, they will survive better and they just there accumulate over time. And so the two great places to look for meteorites are hot deserts, where they won't rust away. And the very best place to look for meteorites is Antarctica, because that's also a desert. It's also a big deep freeze, so it's fantastic for preserving meteorites. And the glaciers tend to move the meteorites around and can dump them in certain areas, so they actually get concentrated in certain places to make them easier to go and collect.
How big are they?
They are all sizes. So extraterrestrial material is falling all around us, Chris. So think maybe up to 40,000 tons a year of material is falling to Earth every year, but nearly all of that is in the form of dust. And then as you get to bigger sizes, they get rarer and rarer. So the meteorites that we pick up in Antarctica, they tend to be from the size of a nut to an apple, maybe. That would be the typical size.
Do you find them by flying over the ice and spotting them, or have you got other crafty ways of seeing them? Because you can't, I mean, Antarctica's huge. You can't just go for a wander around Antarctica to go and find them, or do you?
Yes, we do. Yes.
Really?
Yes. Absolutely. Honestly, it's the most fun you can ever have. It's like a big Easter egg hunt. But yes, because the glaciers can sometimes hit into a mountainside and then the ice will start to ablate away or be removed away by the wind. And any rock that's inside the glacier gets dumped in certain places. So they do get quite concentrated to such an extent that you can go down around either by foot, or we use skidoos as well to drive around the ice.
I can see the attraction now.
Yeah, so fun. Yes, great. Cold, but fun.
How many did you find then?
So there are expeditions that go every year, and they will typically find a few hundred to 1,000 on each trip.
Goodness. And they come back, or they go back to host laboratories like the one you run now, I presume. How do you interrogate them? What do you do once you find a nice meteorite that's 4.5 billion years old? What do you do with it?
We classify it as the first thing that we do, and broadly they can be made of iron or stone, or sometimes a mixture of iron and stone. So there's that very simple classification. But then what we really want to know is where it came from. So one of the problems with studying meteorites is that unlike a terrestrial rock that you might have gone out and done some field work and collected yourself so you know exactly where it's from, we rarely know where they come from. So it takes quite a lot of work, including looking at its mineralogy, looking at its bulk chemistry, sometimes looking at its isotope composition, to work out, firstly, broadly where it came from. So most meteorites come from asteroids, but a few come from Mars and a few come from the moon. So we want to find out which of those categories it's in, or maybe it doesn't look like it comes from any of those categories. And then we want to work out for the asteroidal ones whether it originated from the innermost part of the solar system or the outermost part of the solar system where there was more ice around originally.
How do you know which of those it is?
For the icy ones, they often still contain water, which is trapped inside clay minerals. So that's one of the things that we look out for. We look to see if it has clay in it. Or it may have completely dehydrated, but we still see evidence that it was once there by looking at its texture and composition.
When you look at something like that and you think, I've got something here that's probably 4.5 billion years old. I know when I find fossils on Earth, it sends a shiver down my spine because I think I'm looking at something that, in this case, probably a few 100 million years old at most. But when you've got something that ancient, it must create a sort of a special frisson for you.
Absolutely. So for me, I love every meteorite that I look at. Each one is a little bit different. And I think each one can tell us something new about our origins, about how the planet's got to be here, how we got to be here. And so absolutely, I get excited with every meteorite that I look at. It never gets boring.
How did you end up at the Natural History Museum?
Yeah, so there are not very many places that you can work on meteorites around the world, but the Natural History Museum in London is one of them. It has one of the oldest meteorite collections in the world, and it has a fantastic and very comprehensive collection of meteorites, as well as having a fantastic suite of labs that look at the mineralogy and chemistry of rocks. So it was a really kind of attractive place for me to go to be able to kind of pursue these research interests that I have.
It's slightly a strange question, but it's just occurred to me that, well, how did people back in history know that a meteorite was something special and not just another lump of rock?
Yeah, that's a really good question. So for a long time, people didn't really believe that meteorites existed. And during the Enlightenment in the 1700s, for example, when people were starting to try to get more rational about science, there was actually the intelligentsia at the time thought that meteorites couldn't possibly exist. There couldn't be rocks from space, even though there were lots of folk stories about it. And it was only around 1800 that scientists started looking at these rocks that peasants had claimed to have seen falling in the fields and realised they were all quite similar to each other, that the penny dropped, that actually they really were extraterrestrial rocks.
Once you were installed at the Natural History Museum, what was the furrow that, you weren't a peasant, but what was the furrow you were ploughing with your meteorites from there?
Yeah, so I'm still really interested in how the protoplanetary disk formed, but I became more interested in slightly later history of what happened once an asteroid was there. So by looking at the mineralogy of the asteroid itself, and especially the ones that formed with ice, you can look at how much water it originally had and how the water has interacted with the rocks. And I became interested more in learning about basically how our Earth got to have water on it. And we think that the Earth got all the water from its oceans by being impacted in its early history with asteroids that contain clays. And so I wanted to look more about how that formed and where it came from.
So, brief history of time then. We have this massive cloud of gas and dust, and something kind of buffets it to start under gravity coalescing. It forms a primitive star, which then gets big enough that it fires up. And meanwhile, around its sort of middle, it forms this disk of material that the planets are born out of. But they're all, like the Earth, the inner ones, they're all dry, and they get their water from these asteroids. So why do the asteroids have water, and the planets didn't then?
Yes, so that is a great question. And we've really only quite recently, in the last few years, started to have a big model of how this happened. And it's a crazy idea, but I think could be true. It's probably true, that when the giant planets formed, they probably didn't form where we see them now. They may have moved around. So they may have moved into the innermost part of the solar system and then moved outwards again.
This is Jupiter, Saturn, Neptune, those sort of gas giant planets, not little rocky planets like us.
No, just thinking about the giant planets that make up most of the mass of the planets of our solar system. But these outer planets. So while they moved around, this would have been really disruptive to the small bodies like asteroids and more icy bodies that were around at the time. This would have meant that these smaller bodies kind of were moving around in and out of the solar system, many of them being ejected from the solar system as well. But one of the results of this would have been the ones that formed in the outermost part of the solar system, where there was a lot of ice, so they accreted with a lot of ice, may have been ejected into the inner solar system and then been available to hit the Earth, not just the Earth, but also Mars and Venus and Mercury as well.
Were the inner bodies like the Earth and Venus when they were forming? Was it just too hot then that they blew off all their water, and that's why they were dry and rocky, and they got their water later when things were cooler from these outer solar system bodies coming in with their ice?
Yes, that's our current hypothesis. There are some scientists who think that they may have retained some of their primordial indigenous water, but I think they were probably just became too hot as they accreted, and they wouldn't have had any water at that stage.
This was presumably this work, the prelude, that ended up with you working on the OSIRIS-REx mission, which that's been the real pinnacle so far of what you've achieved, isn't it? Being able to actually lay your hands on pristine samples. You don't have to go to Antarctica. You've effectively reached out into deep space and got a sample of an asteroid to look at.
Yeah, it's been absolute privilege of my career to work on this mission, OSIRIS-REx. So this is a NASA mission that visited asteroid Bennu and collected over 100 grams of material from its surface to bring it back to Earth, which makes it the biggest NASA sample return mission since the Apollo era. So it's a really kind of big deal for the NASA teams. But it was exciting for us, those of us who study meteorites, because, as I said before, one of the things that's really annoying about meteorites is that we don't know where they came from. When I was trained as a geologist here in Cambridge, one of the kind of things that was beaten into us was that we need to do field work. We need to go out into the field, look at the regional geology, and then pick a rock to bring back to the lab for further study. With meteorites, we can't usually do that, but with OSIRIS-REx, we can. That was our field work. We went out to this asteroid. We spent 2 years mapping it, so we really understood its surface in a huge amount of detail before selecting the area that we would sample and then bring back to Earth. And so we have this incredible context of knowing exactly where it came from. And that helps us not only understand Bennu, but it also helps us understand all the other meteorites in our collection as well, because we can look at how it's the same or different to these other meteorites as well.
Why did you pick on Bennu? Why was that the target of the mission? Was it just because it was there, or were there some other features that meant you thought that's a good one to go for?
Yes, so it was in a good place to be able to reach quite easily. It's a near-Earth asteroid, which means that it has an orbit similar to that of the Earth, so that made it more accessible. But also, it was a target because it looks dark. It looked almost black, and that made us think that it might be rich in carbon, which we were particularly interested in because we wanted to use this mission to try to address some of the big questions about how the Earth may have become seeded with organic material.
Has it answered those questions? Because that's the really big one, isn't it? We're all thinking, well, the planet's been here 4.5 billion years, but we've got evidence from your geological and earth sciences colleagues that life got started here pretty quickly. So the question is how? So have you got some insights now off the back of what you're seeing out there in the asteroid belt and beyond that might give us some insights into what could have happened here?
Yeah, so one of the things that really surprised us about the return sample from Bennu is that it's incredibly rich in carbon, and that carbon is mostly in the form of organic carbon. And we knew that we had organic carbon in meteorites, but in meteorites it's really hard to say how much of it is indigenous to the meteorite and how much of it might be contamination, because as soon as a rock comes to Earth, it immediately gets crawled over by worms and bugs, and people will pick it up, and so it immediately gets contaminated. But we knew that we could keep Bennu in a completely pristine state, and so we knew that all of this organic carbon it contained was pristine, and it showed us this incredible kind of zoo of organic molecules. So we found lots of amino acids in there, and we found nuclear bases. So we found really these very biologically important organic molecules, although we don't think the ones in Bennu form biologically. But these would have rained down on the early Earth and surely must have helped kickstart life on Earth. And as well as the organic material, we also found loads of salts that would also be really bioessential. So phosphates, for example. Bennu contains loads of phosphates, which obviously is used here on Earth as a fertilizer and is really an important constituent of all living things. As well as that, we found lots of ammonia, as well as sulfur. So we found really kind of biologically important material, as well as the water. So Bennu contains a huge amount of water that's trapped within the clays that make up most of the rock.
How did the asteroids come by this then? The Earth didn't have it. You've argued that it was hot and a horrible environment here to start with, which would have boiled off a lot of this stuff. But where did the original chemicals come from, or how did they come into existence that are aboard asteroids like Bennu?
Yeah, so we think that Bennu's parent body formed right in the outermost part of the solar system. So there it didn't get heated by the young sun. It would have stayed very, very cold. And so it was really rich in these volatile elements that are actually very abundant in the universe. So going back to the work on nuclear synthesis, so the most common elements in the universe are hydrogen, oxygen, and carbon and nitrogen. And so these are really important elements in Bennu as well. So it accreted from this very kind of primordial material, and it wasn't boiled off like it was in the innermost part of the solar system. But then we think Bennu, in its early history, probably had pods of water, salty water, and these would have been fantastic environments to make more sophisticated organic molecules, like the amino acids, for example, may have formed inside this parent body itself. And so all of these wonderful ingredients for life were being cooked up in Bennu's parent body. Not just Bennu, but also loads of other small bodies around the solar system as well. So these sort of environments were likely very common in the outermost part of the solar system. And all it needed was some mechanism to eject them to the inner solar system, and from there to hit all of the inner planets.
This is really intriguing then. So we end up with the Earth being a potential home, but it's not ideal and it hasn't got things really that it can use to kickstart life yet. But in a much more propitious environment, way out in space, it's much colder. You've got all the raw materials there and they're in a body which can cook them up like a kind of pressure cooker out in space. And then they're conveniently dislodged and chucked at the Earth by other bigger planets jockeying for position and that brings these molecules that have been cooked out in deep space to Earth, where they can potentially trigger life processes.
It sounds almost fantastical when you say it, but it kind of makes sense that the outer solar system would have been this environment full of all of these really important molecules. The planet migration, we think, may happen in exoplanets as well. So that means that potentially these processes are not just limited to our solar system. They may be universal processes that are found, we may discover on exoplanets as well.
Did asteroids like Bennu have a heat source then? Because some of this chemistry can't have happened to make these exotic molecules at the really low temperatures that are out there. It must have needed some heat. So where would that come from?
Yeah, so there were some radioactive isotopes around in the early solar system. So probably the most significant example is aluminium-26. So this is a radioactive isotope with a half-life of just 750,000 years. And this was around in the early solar system. And it could have provided enough heat for asteroids like Bennu to heat up enough, at least, to make liquid water.
And if this chemistry was happening in the outer solar system and then these things were being delivered inwards to planets like the Earth, that adds enormous credence then to the idea that there may have been life processes on Mars as well, because it wasn't just some chance roll of the dice here on Earth. These things were raining in on multiple planets, and if the conditions were right, they could kickstart life processes.
Yeah, I think that's something that the rest of the mission team and I are really believe in, that there's nothing particularly special about Bennu. It is a fairly ordinary asteroid, and we found all of these amazing things in Bennu, and that means there's probably loads of asteroids like that, and they would have impacted not only the Earth, but all the other inner planets as well. And yes, of course, Mars is a particularly target of interest because in its early history it would have been warmer and wetter, so it's very likely that these could have equally kick-started life on Mars.
How does this square with things like the Urey experiments, where he conceived, I mean, this is like half a century ago, that the harsh environment of the early Earth, lots of lightning and the dense atmosphere would have led to also the production of many of these exciting molecules. Do you think that was icing on the cake and it was the asteroids that really did the heavy lifting, or do you think it all contributed?
I think that a lot of these ingredients would have been provided by asteroids, but there's one thing that we haven't seen yet, and that is the spark where life actually began. So even though we see all of these amazing molecules on Bennu, we don't see any evidence that life itself actually started on Bennu. Maybe it needed a planet for that with an atmosphere that would have protected it from radiation. And so maybe there's some role for these sort of Miller-Urey type environments to actually create life with the ingredients that have all been provided by asteroids.
When that sample arrived on your desk, what was that moment like? Because you think that's come from deep space, this bit of Bennu. I mean, presumably you're very careful with that. You don't want to drop that. But what's it look like? And how much of it have you actually got to play with?
So, yeah, it was an incredibly exciting moment to get the sample in our lab. It's been a long time coming. So I've been part of this mission since 2013, and I was there to watch it launch, which was in 2016. So we've been waiting such a long time. What we actually got was a teaspoonful, basically, of little black grains. So probably not very much to look at, to be honest, but still incredibly exciting.
I wonder what Colin Pillinger would have made of it.
Yeah, he would have loved this mission. He would really have loved this mission. He would have loved everything that's happening in planetary science at the moment, including, the exploration of Mars and the potential to get samples back from Mars as well. He would be blown away by what's going on at the moment in planetary science.
He was one of the first guests we had on The Naked Scientist when we actually started the programme, and he was going to launch Beagle. And we actually had him on the programme to talk about it. It's very, very, very nice to have talked to him.
Oh, no way. That's brilliant. Yeah, he was an incredibly inspiring person. I mean, he really kickstarted my career and that of many, many of my colleagues as well. He really had an incredible effect on the planetary science community in the UK.
I remember him famously saying to us, he said, scientists know a lot more about art than artists know about science. I think he was a bit sniffy about his science, but no, he was a lovely chap. But when you're not thinking about asteroids, what do you do to unwind? Because when you've been on a project like this and it's so intense and it's been so exciting, do you not have the bit like David Cameron said when he stopped being Prime Minister. He used a swear word and said, "I'm bored SH1T lists." And he found it really hard to unwind. Do you have that?
I honestly never find it hard to unwind. So yeah, I would, I'm, happy to have a good book, cat on my knee. Also with my family, we go out hiking and we just love kind of traveling and exploring the world.
I bet you have a busman's holiday though, because whenever I go anywhere, I find myself drawn to the geology, and I'm always looking at the geology. I can't just look at nature. I have to see the geology or the biology at work when I'm there.
Absolutely. We went on holiday to Iceland last summer, and that is a geologist's paradise. Like everywhere you look, you see some incredible geological formation. Yeah, it's impossible not to be a geologist if you're there.
Amazing stuff. Sarah Russell, thank you very much, our Titan of Science this week. And in fact, there'll be another Titan next time when we're joined by the director of the Oxford Vaccine Group, Andy Pollard. He's been at the forefront of some of the major vaccine breakthroughs of recent years, including playing a key role in what happened during the recent pandemic. He'll tell us all about it. Now, if you are enjoying the programmes that we bring to you here on The Naked Scientist, do please consider giving us a donation to help keep the show on the road. You can do that at nakedscientist.com/donate. We've made it very easy, very simple, very, very secure as well. It all happens off-site via secure channels. And we're extremely grateful, to say it again, to those of you who do step up and support us each month in some people's cases, or just in a one-off capacity. Every little really helps. Thank you very much indeed. I do try to write back to all of you who are making donations to say how grateful we are. That's nakedscientist.com/donate. The Naked Scientist is actually made at Cambridge University's Institute of Continuing Education, and we're also supported and very grateful to Rolls-Royce, who keep us going as well. I'm Chris Smith, and from all of us here at the Naked Scientist team, thank you for listening this week, and do be sure to tune in next time too. Goodbye.